Hello everyone. We are the Bless Your Soul project design team, and we believe in freedom of mobility for all. Our ability to walk is an intrinsic part of our lives that we sometimes take for granted. As a result of trauma, disease, or degradation, however, spinal cord injury patients are often inhibited from completing the gait cycle, also known as the walking cycle, normally. Spinal cord injuries, categorized as a neurological condition, afflict about 86,000 Canadians. Our design team aims to develop a product to help patients with incomplete spinal cord injuries. Using data collected by the Rick Hansen iSCI registry in 2019, we determined there are about 60,000 users who fit our target profile within Canada. Our team has used this data to build user personas to help build empathy between the targeted users and the design team. Current assistive devices, such as exoskeletons, cost upwards of $50,000 and most do not target the ankle joint. All the forces required for walking are delivered to the ground through your feet. Therefore, engaging the ankle is critical for a natural, comfortable walking motion. Our design team has identified a need for a neurorehabilitative assistive robot technology with tunable support structures about the ankle joint to facilitate gait movement in individuals with an incomplete spinal cord injury. We have identified 5 key functional design requirements to optimize product usability and performance. Our design must provide passive support throughout the gait cycle to facilitate correction of foot kinematics, and active actuation to supply half of the required torque during the push-off phase as highlighted on screen. Our target demographic ranges from the 1st to 99th percentile of users in agreement with industry standards. Ergonomics are a fundamental consideration for a neurorehabilitative device. Our product must incorporate 2 degrees of freedom in the plantar flexion dorsiflexion plane and the pronation supination plane. Finally, our design must be modular to fit a variety of user profiles. We are proud to present the Lockstep, an ankle exoskeleton with passive and active support structures that help the user walk. Our team has been graciously supervised by Professor Arasha Rami and our postdoc advisor Rezvan Naziri. Our mechanical design was shared between Anna for the structural validation and finite element analysis, while Vatsalia and Milos shared the majority of mechanical design and manufacturing responsibilities. Our electrical design was distributed between Taha for the sensor validation and implementation, and Trevor provided the algorithm for the linear actuator. Debrish has been our project management lead throughout the design cycle.
Our design has gone through various iterations as we continuously refined our product scope and functional requirements. Our prototyping process has included a low fidelity to validate form and function, and a fully functioning high fidelity proof of concept with full range of motion and sensor capabilities.
The Lockstep incorporates a linear actuator in the dorsiflexion plantar flexion plane, and a set of passive springs that support the user during pronation supination.
Our mechanical design incorporates a novel spring-controlled slider mechanism that allows the user to rotate the ankle in the pronation and supination axis and increase comfort during walking. Research data shows there is approximately plus or minus 5 degrees of rotation about the subtalar axis during the gait cycle in healthy individuals. Structurally, our team has prioritized a modular design to fit a variety of user profiles. In prioritizing a lightweight design, the team has opted for PLA in non-structurally critical components and aluminum sheet metal in load-bearing items. Because of the complexity of the assembly, FEA was used at a component level to validate the structural integrity of the parts. RBE3 elements were used as connectors with the appropriate forces and moments applied at the bolt holes to identify any areas with high stress that required redesigns. Components with simple geometry were validated using axial stress and buckling calculations to identify and mitigate any risk of failure.
A key objective for our product is to determine the user's position in the gait cycle. This is done by using a linear encoder to calculate the ankle angle as shown in the video on the top right, and also using a set of push buttons to determine the type of foot contact shown in the bottom right. Pairing this data together lets us know at what walking stage the user is at, and the system can then apply the appropriate torque to assist the user. A simple calculation of this is illustrated with the black dotted line shown on the graph on the left. In order to actually assist the user with walking, the following control loop was set up. A variety of end stops and limit switches were implemented to ensure user safety throughout this entire process, which begins with reading the gait position from the sensors. This value is then converted to a related force, which is verified through our current control system. If at any time we detect there is an unsafe amount of current or force in the system, we immediately stop any actuation. Otherwise, the actuator continues pulling or pushing until the next gait position is detected, where the cycle then repeats itself until the user decides to stop.
Through the generosity of Professor Arami, we were able to conduct testing in his research lab. A motion capture system was used to validate the range of motion and speed of gait cycle completion with and without the lockstep. A force plate was used to measure the ground reaction force, leading to validation of the torque supplied by the actuator. Finally, an EMG sensor was also used to capture muscle activity in the calf for both conditions. The results from our tests show that we are able to successfully provide up to 50% of the required torque at the ankle joint while reducing the peak calf muscle activity by 78%. Our design project has advanced our teammates' capabilities in a multifaceted design environment. Our team has been able to expand our skills beyond mechanical engineering by exploring software development, hardware design, and human physiology to complete a well-rounded biomechanical product. In spite of a challenging remote design cycle, the Bless Your Soul team has been able to design, manufacture, and test a working ankle exoskeleton prototype that reaches the team deliverables and constraints. Our product aims to challenge the existing market for ankle exoskeletons and significantly lower the consumer cost to $1,700, which is 25 times less than the current cost of the leading ankle exoskeleton that is commercially available. This will ensure that the delivery of care and participation in Canadian society is no longer limited to the price that a person can afford to pay. In the immediate future, our team has discussed the possibility of further developing our product with the help of our faculty advisors to create a viable consumer product. Our mock-up website demonstrates the modularity of our design for various user profiles. Moving forward, our team is planning to expand to accommodate ACL injury patients. ACL injuries are among the most common injury in sports, and oftentimes surgery can be expensive, risky, and may not yield satisfactory results. Thank you for attending our virtual product demonstration. We are now open for questions.